could not come in person. Okay. Yeah, I'm sorry that I got sick and could not come in person. But I would be happy to stick around after the seminar to answer questions, and also I should be around next week as well, and hopefully then I can actually catch up with people personally. So today I would like to present my work in collaboration with Fedor on measurement-induced phase transitions. Let me start from our motivation. So as you probably heard, in recent years, there were lots of discussions about measurement-induced phase transitions in condensed matter community. And a measurement-induced phase transition is typically abbreviated as MIPT. And this is by accident also the name of our undergrad university where we studied with Fedor. So we felt that we have to write a paper on this. Just kidding. So the upshot of all these discussions in condensed matter community is that physical systems are very often resilient to noise coming from measurements or projections. So the decoherence happens like a phase transition rather than gradually. And people introduced different entanglement diagnostics to probe for this behavior. But today I would like to take a slightly different perspective. Very often measurements are not noise. Instead, they're an important part of the dynamics. One such example are quantum teleportation protocols. And in the context of holography, the two which might be known for people here are Jafferis wall protocol and Kitaev Yoshida. And so the question I would like to ask today, are there any phase transitions in quantum teleportation if I apply these protocols at high rates? So these protocols involve measurements, and then I want to do them very frequently. And the answer I would like to present you today, that in the SYK and JT gravity, there is indeed a phase transition. And in the dual gravity picture, it corresponds to a transition from two entangled black holes to eternal traversable wormhole.
Can I ask you a question?
Of course, yeah.
What do you mean by high rates? I thought if you apply a projection operator to some state, you just project it, you keep applying it again and again,
yeah,
it will not change anything. So, because if I start from
you measure a subsystem.
What?
You measure a subsystem.
Okay, so you're not projecting the whole system.
No, you don't project the whole thing. No, I will describe the details a bit later. But no, every time you project a different subsystem.
I see. Okay. Thank you.
Any other questions about the motivation? Okay, so the plan for today is let me briefly introduce Jafferis wall and Kitaev Yoshida protocols. Then it turns out that the analysis in the Jafferis wall case is pretty simple. And then I will spend the rest of my talk on Kitaev Yoshida case because it actually involves some non-unitary dynamics. And then I will also need to develop some path integral techniques to describe that. So the setup I will be studying today is the following. I have a bipartite system. I have left side and right side. They are prepared in a entangled state, in the thermophile double state. But otherwise, they evolve under independent Hamiltonians. So, and in this case, obviously, there is no causal connection between the two, as can be measured by left-right anti-commutator of fermionic fields. So for bosonic, it would have been commutator. For fermionic, it's anti-commutator. And in these setups, it's identically zero. You cannot transfer any information between the sides. So this thermophile double state For holographic systems, it can be represented as two entangled black holes connected via Einstein-Rosen bridge. So naively, you have a pace of, if you look at this time slices, then naively you have a black hole on the left and black hole on the right. And under the horizon, you have a portion of a space-time. And naively, you can try to say, okay, I can just go between the two. But in fact, you cannot, because as you go forward in time, Einstein-Rosen bridge grows with the speed of light. So at later time, the spatial slice will look like this. So the way you can probe this behavior at the boundary is by equal time correlation function, which decays exponentially. So this exponential behavior signals the linear growth of the length of the Einstein-Rosen bridge. So in the corresponding Penrose diagram, the process would look like this: that I throw something on the left side, it goes under the horizon, but it is never able to reach the other side because this part of the space-time expands too quickly. So I need to modify the dynamics in some way in order to be able to transfer stuff from left to right. One ways to do that, two ways to do that is first introduce an extra unitary which couples the two sides. This is on the left, this is Gauss-Jafferis wall case. So I pick up an operator on each side and I introduce this term into the Hamiltonian. This is will be double trace deformation. Another way to transfer stuff is pick up a random subsystem on each side and project it on a maximally entangled state on a bell pair. And then again, my goal is to make this anti-commutator as big as possible. So in contrast to other measurement-induced phase transitions, this transition will be characterized, can be diagnosed by a simple correlator instead of von Neumann entropy. So in the rest of my talk, I will be studying these two dynamical setups, and I will be computing this correlation function. So yeah, this is the foundation of what I'm going to do next. So maybe I should pause for questions. Because if you have any questions, it's good to ask them now. Okay, let me go forward. So let me jump to the SYK case and consider Gauss-Jafferis wall interaction. So the total Hamiltonian now is written schematically this way. I have SYK Hamiltonian for the left, SYK Hamiltonian for the right, and then I have an interaction term. So I coupled some operators of dimension delta on each side. And then initially this term was off, and then I turn it on at some point in time. So following SYK conventions, in this talk, the actual physical time will be denoted by U, not T. So in fact, we wouldn't need all the microscopic properties of SYK. The only important part is its low energy sector, which is dual to Jackiw Teitelboim gravity. So there is a very nice and very well developed story about this. And the upshot of this story is that in this setup, in the limit of large n, the number of fermions and low energies, there is only one relevant degree of freedom in this problem, which I call L. And it can be thought of as the length of the Einstein-Rosen bridge. So JT gravity, it's 2 two-dimensional gravity. So now Einstein-Rosen bridge is basically just a line, and the only relevant degree of freedom it's the corresponding length. So in this setup,
what is L prime?
It's time derivative.
Okay.
It's time derivative with respect to boundary time. So this is the effective energy, effective Hamiltonian. So the first term is what you get without extra interaction. So as you see, I have a exponentially decaying potential, which pushes length to be as big as possible. So this should remind you this picture that if you allow the system to evolve freely, then the length just increases indefinitely. Interaction between the sides brings an attraction force between the sides of the Einstein-Rosen bridge. So I have this minus sign here. And so now the potential actually has a minimum, which looks like this. And as I said earlier, in this limit of large n and temperatures are much smaller than J, but not smaller than 1 over n, this dynamics is actually classical. It's dominated by saddle point. So which means that I just need to solve classical equations of motion for this Hamiltonian. And it's really a high school physics problem, because I have some initial motion in this exponential potential. And then at some point I quench this extra term. And then I ask if there are any qualitative differences as I increase this mu. And the answer is obviously yes, because if mu is large enough, then the energy after the quench will be negative. So the trajectory will be trapped near this minimum. But if mu is small, then the energy will be positive and the trajectory will still run away to infinity. So basically what we found is that there is a phase transition which can be nicely described in terms of ADS, in terms of trajectories in ADS space. So Jackiw Teitelboim gravity is all about boundary trajectories in ADS. So I have a rigid ADS spacetime, but then you should think about SYK dots, SYK degrees of freedom living on a certain time-like trajectory inside ADS near the boundary. And so if mu equals to 0, then I have two trajectories which start and terminate at the boundary within a finite global time in ADS. So this strip, you should think about it as a global ADS2 space-time and Lorentzian signature. So the light rays are at 45 degrees. And the fact that I cannot send the information is illustrated by the fact that if I send a light ray from one side to the other side, then it's not possible to do that. So it will definitely miss. If mu is small, so I switch it on indefinitely, but if it is small, then still the trajectories will attract a little bit each other. And then there will be a certain time interval in which I can actually communicate between the left and the right. But then at later times, the light ray will still miss the boundary trajectory. So this is essentially Gauss-Jafferis wall computation. So you can also do this in higher dimensions. And this effect is captured just in the leading order perturbation theory in mu. So one thing which we were able to do in JT gravity very simply, as you saw, that at certain critical value of mu, these boundary trajectories, they don't terminate at the boundary anymore. So they just continue along the global ADS, and then I can send a signal at any point in time. So in less geometric terms, I can describe this transition in terms of this anti-commutator function. So what's my setup? I switch on the coupling at time equals 0, and then I insert the perturbation at one side at time equal u1. So this is u1 here. And then I plot this two-point function as the function of capital T. It's capital T is when I probe the presence of the signal on the other side. And so if I switch on the coupling and insert a message on one side at the same time, then sure, it reaches the other side at some point. But the problem is that if I try to do this at later times, then the transport fidelity will be exponentially suppressed. You see, for u1 equals to 20, it's highly suppressed already. So this is a picture for small mu, but above mu critical there is a drastic change happening. So now if I insert a perturbation at any time, essentially, it will bounce back and forth between the sides of the ADS. And then it really does not matter when I do this, there will be just a constant time delay between the two signals. So this solution, where I have two trajectories going on indefinitely, it is not new. This was described by Maldacen and Xi. Our result is that you can actually go dynamically between the thermophile double and this eternal black hole, eternal wormhole solution. So, and it happens in a certain critical mu when you switch on this interaction at some point. So are there any questions before I continue to Kitaev Yoshida? Okay, so many of you might be puzzled by the fact that I promised you MIPT, but so far there were not any measurements in my slides. In principle, adding this extra unitary, it can be given an interpretation of measuring something on one side and then transferring the measurement, the classical information about the measurement on the other side. So you can do this essentially with any unitary, but in the end of the day, what you study is this Hamiltonian dynamics. So now I want to do a real thing. I want to study the Kitaev Yoshida case when I have a genuine projection. So now I want to study this part.
Sorry, I have a quick question about the interpretation. You said you're going to do this measurement at high rate. What is the analog of the rate in this story?
Yeah, I think it should be mu, because mu essentially have dimension of inverse time. You can think about it as how often you perform this measurement. So large mu corresponds to high rate. Okay, let me add a few more comments on this. So this behavior was actually conjectured. So this transition between two black holes and wormhole was conjectured for the BTZ case based on perturbation theory. And then the simplicity of JT allowed us to find the full solution. And the interpretation you can give is the following. So as some of you know, Gauss-Jafferis wall, it introduces negative energy inside the bulk in order to slow down the expansion of the Einstein-Rosen bridge. So in Einstein general relativity, traversable wormholes are allowed only when you violate average null energy condition. And the Gauss-Jafferis wall protocol with inserting operators on different sides does the job. But then you can ask, okay, what if I introduce too much negative energy inside? Then it seems that if there is too much negative energy, then I run into potential problem of lowering the black hole mass below the charge, such that it becomes super extremal. And you can worry about this possibility and ask, okay, is the Gauss-Jafferis wall, if it can lead you to a naked singularity? And at least the case of JT gravity tells you that no, you don't get a naked singularity. Instead, you get an eternal wormhole. One can also study the case when the initially thermophile double state was not empty. It contained some matter excitations inside, and you can perform the same analysis, which also shows that there is a critical mu above which you go into eternal traversable wormhole phase. Okay, I think I'm now finally done with Gauss-Jafferis wall. So, okay, let me study the case of Kitaev Yoshida when I have this projection on bell pairs. So, what's the precise protocol I want to look at? So I consider time interval du, and then at each time interval du, with this probability, I leave the system alone. I don't do anything. So this defines this parameter kappa. Otherwise, so I flip unfair coin, and with this probability, I don't do anything. But otherwise, I pick up a random subsystem on each side, and I project it on a maximal entangled state with this projection operator Pj. So in terms of Majorana fermions, Pj looks like this. So psi left and psi right are Majorana operators. This is a totally physical procedure. You can do this in a lab. So the way you would do this in a lab is the following: that you take this operator, the Hermitian operator I times psi left, psi right, and you measure it. It has eigenvalues ±1. And if the outcome of your measurement is +1, you keep your sample and you proceed forward with the evolution. Otherwise, if the outcome is -1, you throw the sample away and you need to prepare a new sample. So this is a physical procedure which can be done in principle. But the way you would describe it is using a non-normalized density matrix rho tilde. Because since you're throwing away the samples, it means that you don't preserve probability. So it undergoes the following evolution. So the first part is, so this superposition in terms of density matrix, it tells you that these two outcomes are not coherent. So basically at each time step du, you're kind of end up in two different universes which don't talk to each other. Either you did not do anything, or you performed a measurement and kept only one outcome. And here I also suppress the Hamiltonian part.
What does J run over? Does J run over the whole system or a part of the system?
Yeah, it's J runs from 1 to n. So basically what happens is that you pick up one of the n fermions with equal probability. So at each time interval du, you project only one pair of fermion, a random one of the n. And again, if you're thinking about implementing this in a lab, you would prepare many samples of your system, ideally infinitely many. You will do all this complicated procedure, and in the very end, you will evaluate your observables only in the samples which survived all this filtering procedure when you kept only one measurement outcome. So, and it basically tells you that you need to normalize by the trace of rho tilde. So this is this setup is very similar to what people have been looking at in the condensed matter literature. So this is their setup, that they perform measurement but keep only one of the outcomes. So yeah, this dynamics is not Hamiltonian, but it is totally physical. So maybe I should pause here for a little bit in case people have questions about this these dynamics.
Alexey,
Yes.
I don't remember this very well, but in the usual Jafferis case, there is the sign of the coupling that we introduced, right? Which basically, for one sign, you get the you can basically see the other side, right?
Yes.
Is there an analog of that information here?
Yes, I think so. So here kappa can only be positive because it's measurement rate. But you can change the sign here. So in fact, you have if you have 2 qubits, right? Then you have at least 4 maximum entangled states, and you basically need to pick up one particular one. So like in the thermophile double state, this separator, it has non-zero expectation value, and you want to basically project on the state where you preserve this this expectation value. So maybe if I go back, so as I mentioned before, these in the absence of any projections or interactions, this 2-point function decays exponentially. And then what I want to do is a kind of a Zeno effect. So I want to project on I want to pick up one of the fermions and project on the state where this expectation value is actually 1, so that I sort of push the system backwards in time. So this correlator wants to decay, but I keep post-selecting on measurements where this correlator is actually 1. So I want to actually post-select when it's equal to 1 and not -1, because if it is -1, then it will decay even faster. Yeah, this is a direct analogy of this choice of the sign in Gauss-Jafferis wall. Does this answer your question?
Yeah, thanks.
Any more questions? Okay, maybe I should go forward. So you can use a number of approximations, namely mean field, which is totally justified for SYK, and also some extra energy relaxation, because actually measurements introduce extra energy into your system. So I don't want to go into the details now, but I would be happy to talk about it after the talk or next week in person. So you can do a number of approximations and massage the above evolution equation into this nice one. I again suppressed the commutator with the Hamiltonian, but the nice feature is that these projections, they can be recast as a anti-commutator in this evolution for the density matrix. So where operator S is this operator. So this is actually equivalent to doing infinitesimal Euclidean evolution with this operator. So this is, we call this soft projection. So because instead of projecting some of the states to 0, it instead just slashes their norm. And you can argue that like this procedure you can also implement physically in a lab. So this is a nice channel. It preserves hermicity of rho tilde, and it's completely positive. Yeah, the only feature of this, it doesn't preserve trace, but again, we know why it's happening. Yeah, similar coupling was analyzed for Brownian SYK not so long ago by Brian Swingle and collaborators, but there it had a different origin. And just to compare to what we studied previously we essentially added this operator in the Hamiltonian. And so we had this commutator term in the evolution for rho. But now we have exactly the same operator, but it's featured in the anti-commutator with the rho tilde. This is why I will be able to salvage some of the results from the first part of my talk and analyze this case very similarly. So this Gao-Jafferis wall case was just to develop some techniques. So since this evolution is not Hamiltonian, it would be very useful to study Schwingel-Keldysh representation of this. So, and Schwingel-Keldysh technique is actually very easy to explain. So if I have a normal evolution of a density matrix, I need to dress it with the forward evolution on one side and backward evolution on the other side. So this is the origin of this mysterious plus and minus parts on the Schwingel-Keldysh. So in our case, apart from the normal Hamiltonian evolution, I also add this soft projection with S, and S a Hermitian operator. So when I look at it, I can see that if I interpret it as a Hamiltonian evolution, I see that I have two different Hamiltonians now for forward evolution and backward evolution. So they are different, but they are complex conjugate, and so they preserve the hermicity of the density matrix. So if I again use the go to low energies and study JT gravity, then I will have two set of variables now, L plus and L minus. So this is just the SYK Hamiltonian. It's the same for both plus and minus part. But this extra term, it depends on the fermion dimension. It now has a different sign. So I need to study the classical motion again in this for this Hamiltonian now, and I need extra boundary conditions because I doubled the number of my variables. So what are the boundary conditions? The boundary conditions depend on what kind of matrix element you evaluate. So what we want to do is we want to evaluate something like this. You start from thermophile double, you have evolution, and then you act with operator O at some time capital T. And then you evaluate trace of this. So as some of you know, Schwingel-Keldysh contour, its plus and minus sides, they close at some point. So they meet each other. So this meeting is basically means that I have a trace here. So I have plus evolution on the brass side. Sorry, it's cat actually. I have a forward evolution on the cat side. I have minus evolution on the brass side. But then when I evaluate the trace, they have to meet each other because trace means that I have the same state on the both left and the right. So it means that when I actually evaluate an observable, this L plus has to meet L minus. So one boundary condition is that they meet each other. And the other boundary condition is just simply that it should be glued to a thermophile double state. So the solution should be such that when I go along the Euclidean time by beta over 2, these 2 points meet each other. So there is this Euclidean semicircle, which I did not draw. So the only problem is that operator U is not unitary because it contains projections. And so the dynamics is not causal. I will have to find a trajectory L plus and minus separately for each capital T, because capital T affects the boundary conditions. So as I continue forward in time, the boundary conditions will be different at different times. But the nice feature is that I only need to study the classical motion for these 2 Hamiltonians. Okay, this can be done, and interestingly, for delta greater or equal than 1/2, nothing interesting happens. So all the correlators continue to decay, and yeah, it's nothing interesting happens. So for some people who heard my talk at the Muri meeting, then this is where we stopped. But interestingly, for delta less than 1/2, one very unexpected feature happens. So these 2 potentials, they of course has a number of critical points in the complex L plane. So since this is a holomorphic potential, these critical points, they are either minima or nor maxima, they are saddle points. And they are located on different half planes for plus and minus. So very naively, you would want a solution which is time independent, where L just sits on the critical point. But it is not a correct solution because it violates this boundary condition that L plus has to meet with L minus. So the solution where L just sit at the corresponding critical point is not a solution. However, it turns out that if delta is less than 1/2 and kappa is large enough, so kappa is the measurement rate, then a very interesting feature happens. The trajectory actually spends a lot of time near this critical point, and then it goes to the real axis in order to meet with its partner. So phi is actually minus L, and you should think about it as L plus, part of the trajectory, and the complex conjugate one will be L minus. So I start in thermophile double, then I very fast, then very quickly I go to the critical point. I spend a lot of time there, and then I go to the real axis in order to meet with my plus minus partner.
Sorry, what is phi here? What is being done?
It's minus L.
Okay.
Yeah, it's just I changed notation. Yeah, this is the behavior of this. Previously, L was the length of the wormhole. Now you have to be careful about this interpretation because L is, in general, it's complex. But if I interested, for example, in the equal time commutator, or sorry, equal time correlator between left and the right, this can be used as the probe of the wormhole length. So previously, as I mentioned many times, just in the thermophile double state, it exponentially decays, which indicates the linear growth of L. But now, if my measurement rate is large enough, then this correlator, it stops decaying. It becomes a constant. And in fact, the steady state, it does not depend on the initial temperature. So like this behavior, it's all governed by this part of the trajectory between the critical point and the real axis. So in fact, you can prove analytically that at later times, this trajectory will be universal. It will always end on the same point on the real axis. And this point is this effective length of the wormhole, which is now constant. Again, unfortunately, I don't have a very nice geometric gravity picture for what is happening, because the solution is generally complex. But again, I can plot the 2-point functions. So in the regime, when the measurement rate is small, it looks very similar to the small mu case of Gauss-Jafferis wall. That I insert a perturbation at time equal u, and then I plot this correlation function as a function of capital T in order to see when it reaches the other side. And yeah, what is happening is literally the same as in Gauss-Jafferis wall. Perturbation reaches the other side, but then if I try to do it at a later time, then the fidelity is way less. Above the critical measurement rate, I can insert perturbation at any time. So here it's like 50, 100, 200 in dimensionless units. And it will reach the other side after a fixed amount of time, and it will reach it with the same fidelity, regardless of when I inserted it. So unlike Gauss-Jafferis wall case, I will not have this eternal bouncing between the sides of left and right, because I also have an extra projections, which actually introduce dissipation into the system. So there is, when I do the projection, there is a chance that I can actually project out some important information. This is why this correlator eventually decays. But the important feature is that it stays the same regardless of when I inserted the perturbation. So are there any questions for the Kitaev Yoshida case? Okay, the takeaways from my talk are the following. So if you are already given some semi-classical portion of the space-time in terms of the thermophile double and Einstein-Rosen bridge, then it's not difficult to form an internal traversable wormhole. You just take a finite two-sided coupling. You don't even need the Cole Bath for this transition. You just literally add the coupling and you're done. Also, we analyzed Kitaev Yoshida case, and it required us to introduce some path integral techniques in order to analyze it, but this can be done. So you don't have to do numerics. You can actually do analytical computations on the Schwinkel-Keldysh contour. So why people are interested in these dynamics in case of measurements, because potentially it might give novel phases of matter when you not only have Hamiltonian dynamics, but you also introduce measurement projections or quantum feedback. I will talk about it in a minute. And our contributions to this is that yeah, you can use projections in order to sustain a wormhole. So the wormhole phase is one such example. Phases supported by measurements. And unlike other measurement-induced phase transitions, ours can be diagnosed by a simple anti-commutator between the left and right operators. So what are the open questions? Measurement-induced phase transition and entanglement and resilience to noise can be explained via emergent quantum error correction, which was done in this very nice paper. But I don't think we have a very nice explanation for what is happening in our teleportation transitions. Why do we have this phase transition in the transfer rate as we crank the coupling? So one explanation is that you have a gravity dual, and then you have a transition between the different gravity solutions, but it would be nice to also give a purely boundary interpretation. Also, recently, there were a couple of papers studying other types of non-Hamiltonian evolution when you increase the size of your Hilbert space, and then your evolution is either isometric or not. So it might be interesting to study these setups as well in some specific Hamiltonian systems. Yeah, unfortunately, I could not draw a nice Penrose diagrams for the Kitaev Yoshida case because the solution was actually complex. Nobody asked me about this, but it might sound a little bit suspicious that we used complex reparameterizations in order to study this. We justified it two ways. One is you can study the dynamics after a single projection purely in the Euclidean using normal real reparameterizations, and then they become complex when you analytically continue to Lorentzian. And another justification we have is that in large QSYK, you get a very similar equations for reparameterizations, but they are inherently complex. So for example, if you just study a single SYK without extra interactions or measurements or whatever, then the complex SYK, large QSYK dynamics in Lorentzian, it's governed by certain complex reparameterizations. So it might be interesting to understand these solutions better. Is there a way how we can give them space-time interpretation? So it would be interesting also to apply our path integral techniques to actual entanglement dynamics of phase transitions, usual to standard MIPTs, when you have, for example, a transition between areal or in volume or entanglement in certain cases. And finally, interesting question is how can we use our JT results in order to understand the dynamics of high-dimensional black holes better? So it would be interesting to take our solution for Gauss-Jafferis wall case and lift it to higher dimensions to demonstrate that there is a similar transition happening for near extremal black holes as well. And my final slide is the quantum feedback I mentioned earlier. So as I mentioned, this setup, when you do measurement and keep one of the outcomes, it's totally physical, but unfortunately, it's very, very costly. Because as you progress with time, if you keep only one of the measurement outcomes, the probability of actually preserving the sample or having a sample which always yielded measurement outcome +1 is exponentially rare. So, and this is currently hindering experimental realizations of measurement-induced phase transitions. One thing you can do is to say the following. Suppose you have a sample and you want to project certain spin on +1. So sorry, this is missing imaginary unit I here. So suppose you want to project on a state where this operator is +1. Yeah, you perform a measurement. If it is +1, you are happy. If it is -1, it's unlucky. So maybe then you shouldn't buy a lottery ticket this day. But what you can do now is that you know the state of the system, that you know that after the measurement it ended up in a state where this operator is -1. And so you can act with an extra unitary in order to put it in a state you want. So you measure the spin, the outcome is -1, but then you apply manually a spin flip in order to make it +1. So this way, you don't throw away any samples, and the evolution is unitary. You preserve the trace of the density matrix. You don't throw away anything. And yeah, this is some new direction people have been looking at. And so in our case, it would be the following evolution, that now you also perform a measurement of this operator, and you keep the other outcome as well, but you apply an extra psi in order to flip it to +1. And then I think it's an interesting question what happens in this case. Can you use quantum feedback to again sustain a wormhole? Unfortunately, we couldn't find any nice approximation to this evolution operator for this evolution equation. And presumably it will be, we will have to do it numerically, but maybe there are some approximations we just couldn't find any. Okay, yeah, this is all I have for today. Thank you.
Questions?
Alexey, so is there a sense in which you can have a version of the Kitaev Yoshida protocol for a pure state black hole? So what I have in mind is, for example, Alexey and Korkulu, they had this explicit construction of states, and they showed that if you turn on a Hamiltonian that is tuned to the microstate, you can reveal some region in the interior, right? So, I mean, just naively, I would expect that there might be a version of this protocol where you have some projection that is tuned to the microstate, where you can do something like just in the analogy with Jafferis versus.
Yeah, I think it can be done. Let's see, if you just do a projection once on the Korkulu-Maldacena state, you still have expanding black hole interior, right?
Right. I'm not even sure, because in that case you don't have a density matrix. I'm not sure exactly how to implement it.
Yeah, I think it can be done. Yeah, instead of projecting on the maximally entangled state, you project on some partial Maldacena-Korkulu state.
Oh.
Yeah, I think it can be done. Yeah, but we did not look into that.
Okay, if there is no more questions, let's thank Alexey again. So you'll be here next week in person.
Yeah, Alexey, I wonder if you can see me.
Unfortunately, I cannot, but I can hear you, and I recognize the voice.
Okay.
On Monday here.
Yeah, I knew that. It was just scary.
Why would you ask a question?
But I looked normal, right?
Yeah.
Was the
Yeah, apparently my heart was
No, it was
racing
very
fast
big,
getting
like,
from back,
I see.
and I felt a little bit.
So did you
chill.
feel sick and you tested?
A bit. It was a bit chill,
I see.
and then I went